Imagine a star. Not just any star, but a giant, a behemoth of the cosmos, burning brightly in the vast expanse of space. This star has been shining for millions, perhaps even billions of years, a beacon of light in the darkness. But like all things in the universe, it has a life cycle. This giant star is now reaching the end of its life. It's running out of fuel, the very essence that has kept it burning for eons. As the fuel depletes, the star begins to dim, its once radiant light fading. Gravity, which has been held at bay by the star's internal pressure, starts to win the battle. The core contracts, and the outer layers begin to collapse inward. The star collapses in on itself, a dramatic and violent process. The core, now under immense pressure, heats up and the outer layers are expelled into space. Then boom, a supernova explosion. This is one of the most powerful events in the universe, releasing more energy in a few seconds than our sun will in its entire lifetime. A burst of incredible energy, sending shockwaves through the cosmos. The light from this explosion can outshine entire galaxies, visible across vast distances. A sight of breathtaking beauty, a cosmic firework display that marks the end of a star's life. But this is not just an end, it's also a beginning. This is the dramatic end for some stars, a cosmic spectacle that plays a crucial role in the universe. The supernova explosion scatters elements across space, seeding the cosmos with the building blocks of new stars, planets, and even life. A supernova is the most powerful explosion we know of. It can outshine an entire galaxy, a testament to the immense forces at play in the universe. It can outshine an entire galaxy, a brief but brilliant flash that illuminates the cosmos. And from the ashes of this destruction, something new is born. The remnants of the supernova can collapse to form neutron stars or black holes, the densest objects in the universe. The death of a star is not the end. It's a transformation, a recycling of energy and matter that fuels the ongoing evolution of the universe. A recycling of energy and matter, where the elements forged in the heart of the star are spread across the cosmos, becoming part of new stars, planets, and even life itself. It's a key part of the universe's grand story. The life and death of stars drive the cosmic cycle of creation and destruction, shaping the universe as we know it. A story that continues to unfold, with each star's grand finale contributing to the ever-evolving tapestry of the cosmos. Stars are born in giant clouds of gas and dust. We call these nebulae. These vast regions of space are often referred to as stellar nurseries because they are the birthplaces of stars. Within these nebulae, the conditions are just right for star formation. The gas and dust are remnants of previous stars that have exploded in supernovae, scattering their material across the cosmos. Over time, these materials coalesce under the influence of gravity, creating the perfect environment for new stars to emerge. Gravity pulls the gas and dust together. The cloud heats up. It starts to spin. A protostar is formed. This spinning motion is crucial as it helps to flatten the cloud into a disk, with the protostar at its center. The material in the disk continues to spiral inward, feeding the growing protostar. As the protostar accumulates more mass, its core temperature rises, setting the stage for the next phase of its evolution. Over millions of years, the protostar gets hotter and denser. The pressure in its core increases, causing the atoms to collide more frequently and with greater force. This process of contraction and heating continues until the core temperature reaches a critical point. At this stage, the protostar is on the verge of a dramatic transformation. Finally, nuclear fusion begins in its core. This is the moment when the protostar becomes a true star. Nuclear fusion is the process where hydrogen atoms combine to form helium, releasing a tremendous amount of energy in the form of light and heat. This energy counteracts the force of gravity, stabilizing the star and allowing it to shine brightly. Hydrogen atoms fuse to form helium. This releases enormous energy. A star is born. The newly formed star enters a period of stability known as the main sequence. During this time, the star will continue to fuse hydrogen into helium in its core, maintaining a delicate balance between the inward pull of gravity and the outward pressure from the fusion reactions. For billions of years, the star shines. It remains in this stable phase, radiating light and heat into the surrounding space. The length of time a star spends in the main sequence depends on its mass. More massive stars burn through their fuel more quickly and have shorter lifespans, while smaller stars can remain in the main sequence for much longer. It fuses hydrogen into helium. This fusion process is the source of the star's energy and is what makes it shine so brightly. The core of the star is a hot, dense environment where these nuclear reactions take place, producing the energy that we see as starlight. This is a star's main sequence. It's a period of relative stability where the star spends the majority of its life. During this time, the star's structure remains relatively unchanged, and it continues to shine steadily. Our sun is in this stage now. It has been shining for about 4.6 billion years, and is expected to remain in the main sequence for several billion more. The sun's stable energy output is what makes life on Earth possible. But all stars eventually run out of fuel. When a star exhausts its hydrogen supply, it can no longer sustain nuclear fusion in its core. This marks the beginning of the end for the star, leading to dramatic changes in its structure and behavior. What happens next depends on their size. Smaller stars, like our sun, will expand into red giants before shedding their outer layers and leaving behind a dense core known as a white dwarf. Larger stars, on the other hand, may explode in a supernova, leaving behind a neutron star or even a black hole. The fate of a star is determined by its mass, and each path leads to a different, fascinating end. Massive stars live fast and die young. When they run out of hydrogen, they start fusing heavier elements. Helium to carbon, carbon to oxygen, all the way to iron. Iron fusion doesn't release energy, it consumes it. The core collapses in a fraction of a second. The outer layers of the star explode outwards. This is a supernova. Supernovas are incredibly bright. They can be seen across vast distances. They release huge amounts of energy and matter into space. This material will eventually form new stars and planets. During a supernova, the core of the star collapses. The protons and electrons in the core are squeezed together. They combine to form neutrons. This creates an incredibly dense object called a neutron star. Imagine squeezing the mass of the sun into a ball just a few miles across. That's how dense a neutron star is. A teaspoon of neutron star material would weigh billions of tons. Neutron stars spin incredibly fast. They can rotate hundreds of times per second. They also have incredibly strong magnetic fields. Billions of times stronger than Earth's magnetic field. Section 5. Cosmic lighthouses, neutron stars. Some neutron stars emit beams of radiation from their poles. These beams sweep across space as the star rotates. If a beam happens to point towards Earth, we see it as a pulse of radiation. These pulsating neutron stars are called pulsars. They are like cosmic lighthouses. Their regular pulses allow us to study them in detail. Pulsars are incredibly precise timekeepers. Their pulses are so regular that we can use them to study gravity and other fundamental physics. Section 6. The fate of giants. In the vast expanse of the universe, stars are born, live, and eventually die. Among these celestial bodies, the most massive stars have the most dramatic fates. These giants, after exhausting their nuclear fuel, undergo a series of transformations that are as fascinating as they are violent. Not all neutron stars become pulsars. Some are quieter. These silent neutron stars, though not as flashy as their pulsar counterparts, are equally intriguing. They are the remnants of supernova explosions, the cores of massive stars that have collapsed under their own gravity. They fade from view over millions of years. As they cool and lose their energy, they become less visible, blending into the cosmic background. This slow dimming process is a testament to the immense timescales over which astronomical phenomena occur. But their immense gravity still affects their surroundings. Even as they fade, neutron stars continue to exert a powerful gravitational pull, influencing nearby stars and gas clouds. This gravitational influence can lead to the formation of new stars and other cosmic structures. If a neutron star is part of a binary system, it can pull material from its companion star. This process, known as accretion, can lead to dramatic changes in both stars. The material from the companion star spirals inwards, forming a disk around the neutron star. This material forms an accretion disk around the neutron star. The intense gravitational forces at play cause the material in the disk to heat up to extreme temperatures, emitting powerful X-rays that can be detected by telescopes on Earth. As the material falls onto the neutron star, it heats up and emits X-rays. These X-ray emissions provide valuable information about the properties of neutron stars and the extreme conditions in their vicinity. Some neutron stars eventually collapse further. This collapse can occur if the neutron star gains enough additional mass, either through accretion or a merger with another star. If they are massive enough, they can become black holes. These black holes are the ultimate fate of the most massive stars, objects so dense that not even light can escape their gravity. Objects so dense that not even light can escape their gravity. Black holes are among the most mysterious and fascinating objects in the universe, warping space and time around them and challenging our understanding of physics. Section 7. From death, life springs. Supernovas and neutron stars may seem like destructive events, but they are essential for life as we know it. The elements forged in the cores of stars are scattered into space during these events. These elements include carbon, oxygen, nitrogen, and all the other elements that make up planets and life itself. We are all made of stardust. Without supernovas and neutron stars, the universe would be a very different place, a place without the building blocks of life. Section 8. Star stuff. We are connected. The death of a star is not the end, it's a new beginning. The material scattered by supernovas and neutron stars will eventually form new stars and planets. This cycle of stellar life and death has been going on for billions of years. It's a beautiful reminder that we are all connected to the cosmos. The atoms in our bodies were once part of stars. We are star stuff. And when we die, our atoms will return to the cosmos, to be recycled and reborn in new stars and planets. Section 9. The universe. A stage for stars. Stars are the fundamental building blocks of galaxies. They light up the universe and drive its evolution. Their births, lives, and deaths are all part of a grand cosmic cycle. The next time you look up at the night sky, remember the amazing journey of stars, from their fiery births to their spectacular deaths. And remember that we are all part of this incredible story. The universe is a vast and mysterious place. But thanks to science, we are beginning to understand its secrets, and what we are discovering is truly awe-inspiring.